Okay, let's start with our session today. I'm going to put here, those of you who don't have, please pick one of each of the diagrams here. Okay, so we are going to discuss a bit about basically the issue of water. Okay, let me check the plan we had, the tentative plan. Okay, it's here. Now you should have, according to schedule, should have seen a bit about separation, vertical, horizontal separation, separation for gas with some liquid, separation with liquid for liquid with gas, and also a bit about oil-water separation. Okay, so now we're on the part on water content in natural gas, and we're going to talk probably next week a bit on dehydration. Just to remind, where are we now in the process? Okay. So we basically have here we made the main separation, okay, of oil, gas, and water. And this water that came out is actually free water. Okay, water that came, we're going to see now, from different sources, but it's water that was already mixed with, was free water with the oil and with the gas. But when we take the gas further to any other things, for export, we want to compress it, we want to inject it, we want to sell it, that gas still has quite a lot of water in content. That means that any change we make in pressure and temperature might cause water to come out of solution. Okay, water simply to condense from that gas. And that can cause a lot of issues downstream. We're going to see only a few of these issues, but it can cause corrosion, can cause hydrate, can cause scaling, can cause many, many things. So the main idea is to try to, what we are focusing here first is how this water came to be, right, in this gas, why this gas has water, and then to try to quantify how much it can contain, okay, how much does it have. And probably you had some classes on, it is the same, very similar process to when we calculate the amount of water simply in air, okay, in atmospheric air. You know, when it gets, for example, cold in the morning, sometimes you get some, so you get some water, some condensation on the windows, okay? So it's basically the same thing, but we have to have a method. Oh, I didn't put here. Oh yeah, we have to have a method also for pressure and temperature. Now we are at atmospheric conditions. The pressure is not changing, right? The pressure is constant. When we are in a production system, pressure and temperature are changing both along the production system. Okay, so we have to take that into account. So for that, so let's say one assumption that we typically made is that gas is always saturated with water. Okay? That means that it cannot take any more at a given pressure and temperature. Okay. And that has partly in the reservoir, gas is coming from the reservoir, and it's also coming from oil. Okay, but when it's coming from the reservoir, if we look at the rock, okay, we know that many reservoir rocks they are water wetted. Okay, that means that they have a layer of water wetting the rock, and they might have even some water saturation. But then you can have also oil, but let's make it simple. You simply have gas in between. Okay? And due to the process of being there millions and millions of years, simply it is fully saturated. It already took all the water that can be taken from the reservoir. The gas is fully saturated. It cannot take anymore. Okay, so we avoid that issue to say, well, we haven't achieved yet full solubility. The gas has everything that it can contain. Okay, and as the pressure and temperature change, simply that solubility is going to change. With pressure and temperature changes, okay, the water solubility in gas will change. Okay, typically it's not always rule of thumb, but if temperature goes down and pressure goes down, simply have less, the gas can contain less water. Thus, it has to drop some of the water it has because it cannot carry anymore. Okay, it has reached its maximum capacity. Okay, so let's put here typically with pressure reduction and temperature reduction, the solubility is decreased. Okay, that means that water comes out of solution. Okay, that becomes free water, what we call free water. It's not anymore in vapor phase, but it's now in a liquid phase, and then that causes some issues. Okay, so let's put here some can cause some issues. Okay, and one of the most important is corrosion. Okay, if we have water in contact with metal, unprotected metal, then we can have corrosion. Corrosion causes the reduction in thickness and eventually causes a leak, which we don't want. We are very afraid in the oil industry from a leak. Okay. We can have also a problem called hydrates that we are going to see if we have time today to cover through it. But basically, is this water reacts in the gas in a way that it causes something like a blockage, like an ice. That was a lecture we had last week. The guest lecturer was talking a lot about hydrates. Okay, we can have some other issues, such as slugging. That is in transportation lines, pipelines. Okay, and that means basically slugging means that if you have your pipe at any position that you look on the pipe, you see you have Q of gas versus time. So you have initially a batch of gas, no gas, a batch of gas, no gas, a batch of gas, no gas. Okay, so it comes in slugs. That is caused partly because in the some positions in the pipe, if you have liquid, if you have this water coming out of solution, it's going to block the pipe. Okay, in some places, and then the gas who is in the back is going to push, increase the pressure, and flushes the gas out, and then the process is repeated. The liquid is accumulated, the gas is pushing, and then you get a profile like that. Very bad. Okay, process engineers, everything that we have been discussing here in class is assuming pressure and temperature and rate are constant. Okay, if then you have a change in rate, can cause a change in pressure, temperature, we are in trouble. Okay. Another problem that can bring is issues is, for example, scale. Okay, this you have precipitation of, when you have water, you have precipitation of these minerals. When pressure and temperature change, or maybe when you mix water from different sources, the solubility of these minerals, they change, and they also precipitate, and they tend to deposit on the pipe wall. Okay, and they tend to plug things. If you have a choke, then doesn't work properly. If you have a valve, doesn't operate properly. Okay. What else did we say? Okay, so there are different, that's why just some motivation why, just intuitively what will happen. Water comes out of solution, okay, then can cause a lot of issues that we have to be careful. That's why we want to calculate. So it is we need a way to estimate the expected free water, okay, and the water content in the gas. Again, that's why that's very important for what we mentioned before. Okay, when you send it further, this gas, you have to be sure that you're not going to have this dropout of liquid, of water along the lines. Okay, it can be two things. You can have the condensate, okay, some hydrocarbon is dropping out of that gas, but you can also have water. Okay? And water can cause all of those issues in any pipeline, can have corrosion, all kind of problems. So we want to really to predict, to estimate the expected free water in the gas at any position of the production system. So we are going to go through two methods, okay? Or we are going to, there are basically two methods that people use, okay? One of them is correlation. Okay? People made measurements in the lab, people made measurements in the field, and they developed some expression, okay? Doesn't have to have any physics. Can be, they saw the trend, it's a straight line, we put a straight line. We see the trend is a polynomial, so that's expressions, mathematical expressions derived from measurements in the lab, okay, or in the field. You can also make measurements in the field. And these expressions are often not based in physics. Okay? Like in physics, let's say you start many things, you start with a conservation, either mass balance, momentum balance, energy balance. You find your shape of your equation, and then you try to change the constants that you have in your equation. Okay? Sometimes that's not the case. Simply they plot, okay, they see the trend, one parameter, and then they see it does something like that. Well, I just put there a straight line. I don't care if that has physics, nothing, I just put a straight line. This is not the first time you hear about correlation, right? No? Okay. Good. So, and one of the disadvantages of that, so the advantages, is that it's typically is easy to use, low computational expenses, low computational expenses. Okay. However, the disadvantages is that they are limited in applicability. Okay, let's say they did measurements and they did it for pressures between 10 bar and 50 bar. Okay, and did between temperatures between 10 degrees Celsius to 90 degrees Celsius. If you want to test something that is for 100 bar, or if you want to test something that is for 120 bar, you cannot guarantee that it will give you a good solution, because it was calculated, this expression, for a given range. Okay, it might be that if you increase the range, okay, might be that now you have a non-linear behavior. You have simply it changes trend. Okay, so that's so it's a limited range of applicability. Okay, and sometimes also you have to be careful with the accuracy. Okay, sometimes people they say, well, we want to make this x and y, and but we have a bunch of points, something like that, and then I just put a trend line. Okay, you're going to have some deviation because that was the value measured. I tried to make an approximation, but actually there was some significant deviation between that expression and the measured value. Okay, so if you use it for your particular case, you should also take that into account. Okay, usually correlations they have some sort of accuracy. They take 3%, 10%, 20%, okay, depending on the case. The other approach is simply using an equation of state. Okay. And in this equation of state, you have already seen the procedure, right? We have either Penn-Robinson, we have Redlich-Kwon, we have van der Waals. They make an equation, they find some coefficients that are for the mixture, okay, trying to weight the critical properties of each, and then they use that to predict properties, okay, to predict. The main issue is that they have, if you use it out of the box without any change, they are not so accurate out of the box. Okay, simply you take it with all the default parameters and you use it simply like that. Is usually not very accurate. Okay, you have to make some changes. Remember in class we said, and what kind of changes are those? Okay, in our class we, let's see if I find it here. Okay, remember you had, for example, this okay, that was the equation, the Penn-Robinson equation of state, right? We did it for 3 components. Now you will have water in one of them, but the predictability is not very good. Okay, let's say plus minus 20%. If you want to improve that, you have to change something to make it closer to the measured value, if you have measurement. Okay, what people change typically if these binary interaction parameters. Okay, if you remember on the equation, let's open that exercise. Okay, we have here our EOS part, and if you remember, these beeps, okay, are to calculate this A of the equation. Okay, the A. Okay, this A of the equation, this A that goes in front of this set. Okay, you needed to have these beeps, okay, which we call binary interaction parameters. Okay, A and J. And if you use it by default, maybe it's not very good, the predictability. Okay, so if you adjust it slightly, then you get much better precision, much better accuracy. Okay, so that's typically what is done in the equation of state to try to improve. Not so accurate out of the box, is more general for a wide range of conditions. Okay, it's not limited to the conditions where you develop the correlation. You can take it either for outside of these limits, okay? But are usually customized with experimental data, okay, and typically is by adjusting the default BIPs, okay, binary interaction parameters, and I'm just going to put the equation here. Okay, so you try to change that until you get a very close, until the values are very close. And if you want, so I suggest I have put here on the reference material, you have version 3. Okay, you have a lot of versions. Okay, but now I have added one more chapter at the end, which is chapter from the monograph of Professor Whitson. Okay, chapter 9. So I suggest you take a look at it, and we are not going to go through the whole chapter. Okay, that chapter is about water and hydrocarbon. So there are many things that I have to take into account. Also, gas can be dissolved in water. Okay, then you can have oil dissolved in water, water dissolved in oil. So you have many different things that we are not going to cover here in class. We just want to give you the most important, which is water and gas. But really this is very complete and has a lot of interesting discussions. But on the EOS part, you can read more if you are interested. I think it's section 9.3. Okay, EOS predictions. 9.3. So I'm going to put that here for more information. Of the monograph of Curtis Whitson. Okay, but be aware that you cannot always guarantee that EOS is the best. Okay, sometimes you have to make some adjustment to the EOS. It's good to make some adjustment, and typically the HYSYS, this table is taken from HYSYS. Okay, typically process simulator, equation of state simulator, they have, let me see if it fits here. No. Okay, have a recommended range of applicability of each equation. Okay, so it tells you depending what kind of system you're trying to simulate. Okay, it tells you which equation to use, but it also may give you a warning. Okay, you might have to customize this equation or limited range. Okay, and you have here some examples. We're going to be using we're going to be doing next week an example on tech dehydration. Okay, so then we are going to have to look a bit into that. So that's like another note. Review. Okay, there are some equation of state because of the way they are built. Okay, usually if you remember Penn Robinson, you had two terms. One was, or van der Waals, one was attractive and one was repulsive. Okay, so depending on the way these equations are built, sometimes some of them are better at capturing some components than others. Okay, when you have water, that's a very polar component, so it has some kind of charge repulsion and charge attraction. Okay, so on the correlation side, Okay, we are going to deal with that, but next week, okay, using the equation of state. You're going to use HYSYS for that. But now we are going to be using today and tomorrow basically correlation. Okay, the way correlations were made is basically following the same principle black oil properties. How many of you know about black oil properties? None of you? Really? No? Not even one here, no? Okay. So black oil properties is an approach or black oil formulation is an approach used by petroleum engineers to avoid having to, when you don't want to use an equation of state. Okay, remember the limitation, they take time to run. You have to have these loops, the Rachford rise, you have to have the set calculation of the root, and then you have to have the fugacity loop. So you have too many things just to calculate one number. So they came with this approach, especially used very much during the early stages of the industry, the 50s, 60s, 80s, 90s, and is still very used today. Okay? That is called the black oil formulation. So in the most general sense, if you have at any pressure and temperature, if you have the fluid, let's say we're going to talk first about oil and gas. Okay. So what we do is that we take that fluid, first at that particular pressure and temperature we separate. So I'm going to talk about the most general, okay, which is the modified. So I take both of them separately, and I take it two standard conditions, P standard condition and T standard condition. Okay, so I separate, I'm still at the same pressure and temperature, but now I separate. I just put the gas and the oil separately. And now I send it to standard conditions. Okay? And that might simply imply having a container, keeping the composition constant, and simply expanding, okay, to reduce pressure and reduce temperature. Or that sometimes means passing it through a surface process, which is the surface process we have in the field. Okay. How this P looks like? This P is a series of stages, like you have already learned. Okay, we have a series of stages where finally you have Q gas and Q oil, okay, at standard conditions. That's what this box has inside. But if I want to keep my life simple, I simply take exactly the same, and then I calculate at another pressure and temperature at the same composition. And what I'm going to find some oil, okay, and some gas that come from the oil. Okay, let me put here, that's just an example. An example of P if I have 3 stages, okay? And I get 2 things, okay, from the oil. When I do that to the oil at any pressure and temperature, I get the volume of the oil, volume of surface oil from oil. Okay, that oil came from this oil that I have at this pressure and temperature. Okay, so I say that's the volume of oil from the oil. And now I get the volume of surface gas from the oil. Okay, I got some gas with that oil, so I call also that VG. It has the bar because the bar means standard conditions. That gas and that oil, they are both at standard conditions. Okay, and then I come, and then petroleum engineer likes to find a way to make the relationship easy. Okay, typically I measure in the separator, I measure these two. Okay, and then I want to calculate what are the local conditions, what are the volumes at any given pressure and temperature. With the volumes, I can calculate pressure drop, I can calculate erosion, I can calculate temperature calculations, I can do many things, but I need the volume to get the velocity. Okay, so petroleum engineers simply define a property called oil volume factor, which is simply the volume of oil divided by the volume of oil from oil, and the factor is called BO. Okay, so it's a ratio between, if I take this oil that I have currently here and I take it to surface, then it's going to change. Okay, so the ratio between these two volumes is what I call BO, and that's a function of pressure and temperature. So what do you think that happens when I take this oil to surface? It has gas, right? So it's going to vaporize, it's going to release a lot of this gas. Okay, so what should be the ratio between these two volumes? Should it be bigger than 1 or less than 1? This volume, you just told me, is always bigger than this volume, right? Okay, that means that this factor is typically always greater than 1. And actually has a number maybe between 1.1 and maybe even 1.8. Okay, meaning that the volume of the oil at any pressure and temperature, let's say we say at the reservoir, it can be twice the amount that you have at the surface. Then we make also another factor called RS, and that's the solution gas oil ratio. And that's how much gas was liberated at that particular pressure and temperature. How much gas was liberated here. And here we have BGO divided by BOO. Okay, the volume of the gas at the surface divided by the volume of oil at the surface that came from this oil that I have here. And this value depends, but it is typically something between maybe 80. If we talk about also heavy, this is heavy crude, and this is very light crude. 80, and then might go all the way to maybe 1,000. Very volatile. Okay. So and then I do the same with the gas. Okay, I come and I do the same with the gas. The gas, I come and pass it through this surface process that, remember, can be just simply expanding on a piston. You have it on a piston and then you expand it. Okay, so this P can be examples of P. Let me put it here to the left. Can be, or simply if you have in a lab, okay, you have your conditions, your oil at any given pressure and temperature. Okay, and then you take it to standard conditions, you simply expand the piston. You take the piston up, and then you're going to get from here this much of gas and this much of oil. Okay, two simple process. If you are in the lab, you perform this calculation. If you have an equation of state, if you have a simulator, then you use this process. Okay, with gas we get exactly something similar. We get gas from the gas, and we get oil from the gas. Okay, so we're going to say the oil from the gas, surface oil from the gas, and here is the surface gas from the gas. So the first one tells you where that oil and gas are, and the second tells you where it came from. Okay, it's like the first name and last name. The last name saying which family, okay, which family is coming from. Now with these two new numbers, and this will be VG, I create two more factors. A petroleum engineer like their factors, okay, they enjoy very much their factors. So gas volume factor, BG, and that is volume of gas divided by volume of gas from the gas. And how is that number? What happens with gas with pressure and temperature? For high pressure and temperature, it takes less space, right? It takes very little space. But if I reduce the pressure and temperature, it grows, right? So this number is always much, much bigger than this number. So this factor is typically something between 1 minus 4, maybe even can go to 1 to the minus 2, but it's something very, very small, because that tells you the ratio of expansion of the gas. And then I have finally the solution oil-gas ratio that I take with the RS, small rs. Okay, some people use the letter RV to avoid confusion. So they say that's the volume of oil coming from the gas divided by the volume of gas coming from the gas, which is a ratio similar to what we have done here. It's this number. Okay, so now that we did that detour, okay, let's say black oil properties are usually generated by lab measurements. You take a sample of your oil and your gas, and you make these experiments with a piston typically, and then you find how do they behave. Okay, and to find, I don't want to go how they look like, okay, with pressure and temperature. Just see that you have a ratio, and that's very practical, because if you have a volume that you measure in the separator here, you can know exactly how to convert it to local volumes of oil and gas. Okay, you have the ratio without doing any equation of state calculation, doing any equilibrium calculation, nothing. You just use the ratio that is computed on a table. Lab measurements, you can use a correlation. Okay, people were doing measurements of this black oil all over the world. So we have one very famous here in Norway called Glasse. For example, Glasse. Okay, We have another standing correlation professor he made in California. We have some for the Middle East. We have all kind of correlations that can be used. Okay? Or you can use an equation of state. You can use an equation and a simulator to produce that for you. You take your mixture at any pressure and temperature, separate and calculate these volumes. Calculate the ratio. Then go, change pressure and temperature, calculate again the volumes, calculate the ratio, and repeat for many, many calculations. Okay? So now after that detour is done, we say for water, a similar approach is used. Okay. First, we have some water. Okay, we have at any pressure and temperature. And then we take that water. The surface process doesn't matter very much, okay, but we have to take it through something, even though if it's simply expansion. And then we go here at pressure, standard conditions, and standard conditions. Okay, then we get some other volume. Then we say this volume of water, bar, and volume of water. Okay, and I can define the water volume factor, BW, and that will be BW divided by BW. Okay. What happens? So which volume is bigger? The one to the right or the one to the left? Okay, the one to the right, right? If you see that you have a tank, and you probably have done this experiment sometimes before, okay, and you have some water, okay, with a piston that can move up and down. If you put a person, doesn't move much, right? But then you put an elephant on top of it, it's going to move a little bit, not much, but it's going to compress a little bit. You have some compressibility. So due to the compressibility of water, this BW is always slightly bigger than 1. Okay, not much, but it's 1.01 something. Not much, depending on the pressure, but it's always slightly bigger than 1. Then we can create, besides this BG, if we take simply this gas, okay, and I take it to surface, and now it's going to become slightly complicated. Okay, that gas, like we mentioned before, gives you, okay, here we have BG. Here we have volume of gas from the gas, right? Then we had volume of oil from the gas. And then we have volume of water from the gas. Okay, we can do the same. Take the gas, expand it. Now it's going to release not only oil, but it's going to release water. Okay, and that's what we are looking for in this class. We are looking for how much water drops out of the gas. And then we come and create another factor called solution water gas ratio. And that will be RSW. And the definition is BWG divided by BGG. If I take that gas to the surface, It's going to give you some amount of gas and some amount of water, and I simply divide these two, the amount of water that I obtain by the gas that I obtain. Okay? So in the one of the pages you have, that's the first chart. That was all of that story was just to introduce you to this chart. Okay? So that chart was made by two, published by the Gas Producer Association, okay, GPSA, what you have there on the right, and that tells you exactly that factor, okay, the factor of water, but it doesn't tell you volume, okay, we have to convert later. But it's the water at the surface on the y-axis. Let me pull it up here. Okay, that correlation, people made a lot of measurements and came up with this chart, and it's basically consistent with the way petroleum engineer has worked for a long time. So you have here that factor, but now instead of volume, you have weight. Okay, you have mass, you have kilogram per volume that we can change very easily, right? With the density, we simply change it. Okay, so this is, if you have RSW, that is standard cubic meter by standard cubic meter, right? So how do I change it to the units that I have here? Milligram per standard cubic meter. How do I change it? Okay, simply RSW times the density of the water at standard conditions. That water is at standard conditions. That should give you in kilogram per standard cubic meter. Okay, so that's exactly what is being plotted here. RSW times density of the water. Okay, and this density we assume is 1,000. Okay, so how do we use this chart? Okay, it tells you that factor. Actually, we can make an exercise. Okay, we are going to finish class in about 15 minutes. Okay, because I have to go to another meeting, or maybe 20 minutes. Okay, so we don't take a break. Sorry for that, but then you leave early and we meet tomorrow. I hope that's okay with you. Okay, so let's make an exercise. Try to make it very quickly. It's on my website. But let's try to solve it here in class, and then you can go and access it. Okay, so we have the following system. We have gas, which is the molecular weight very close to methane. We don't have any contaminants. You're going to see that the salinity, the CO2, and the H2S, they affect this solubility. Okay? For example, if you have CO2 and H2S, they like very much water. So if you have them in the gas will have a higher water solubility than if it doesn't have it. Okay? But we are not going to neglect that for now. So we have at different locations, reservoir, wellhead, downstream of the choke, and separator, we have pressure and temperature. And we want to see how much water is contained in that gas. If I take that gas to surface, how much water is going to give? Okay, what is the ratio? So let's do first, let's say the first point. Okay, so let's see here on the chart. Let's put here class exercise. Okay, so we go to the first point. We know that's a reservoir. Okay, and so at P reservoir and T reservoir, how much do I get? So you go on the chart. I think I have to make it bigger. You can do it, and you can also help me if I make a mistake with the chart you have on your hand. So you see 90, here we have 80, 80, 85, 90, 95. So 90 is exactly here. Now we move up, and we have to knock with reservoir pressure 276 bar. However, the chart is in kilopascal. So how do I change from kilopascal to bar? Simply multiply by 100, right? Or not? If I have 273 reservoir pressure is 276 bar, how do I change it to kilopascal? 1 bar was 1 e to the 5 pascals, right? Therefore, 1 bar is 100 kilopascals. Yes? Make sense? Okay. So I get 27,612. Okay, so I should be between the curves. There are two curves, 20,000 and 30,000. Okay, so I go up, put it in red. Okay, and I have to knock it between exactly here, okay, to that pressure. And then I move to the left. Okay, and I'm getting, at least on this, I'm getting 3,500 milligrams of water per standard cubic meter. Yeah, is that what you get also? Okay. So now we want to change it to, we know that's Rs times density of water. Then we divide by 1,000. Then we get 3.5 milligram. Standard cubic meter. Oh, wait. We have to do something else, right? We have to change from kilo to, because the density is in kilo. So we have first to make, again, you have to be careful also. The standard conditions that are listed here are the standard conditions of my field. In many parts of the world is the same, but for example in Brazil they use 20 degrees Celsius. So if you are working in Rio de Janeiro, drinking caipirinha, you have to be careful to use 20 to get the chart for 20. So here we have 3.5 kilogram. Okay, and then we have 1,000. Sorry, 1,000 should be here. How do we do it? We say, if we want to take this to kilogram, it will be simply like that, right? And then I say RSW will be equal to 3.5 divided by 1,000. Sorry, this is kilogram Okay, so these two, they cancel each other, and at the end I end up with RSW is simply 3.5 e to the minus 3 Yep. Okay, simply what I have done, I changed this number to kilogram, right, to have it in the same units as the density. Then I divide by the density, then I cancel kilogram, I end up with this volume ratio, 3.5 e to the minus 3. A unit that is typically used is for this RSW, is typically expressed in standard cubic meter per million standard cubic meter of gas, because it's usually a very small number. Okay, so they like to express it in terms of million. Okay, so how do we change this unit to million? We can say 1 million is equal to this unit, right? 1 million. Okay? Yes? Okay, and then we end up with standard cubic meter per million standard cubic meter. This M is in the SI system. It stands for mega, okay? So that's some water that we have to handle, okay? It was yeah, so that's some water that we have to handle. If we okay, so let's write that on our finally. So we can say here, after all of that detour, right, that this unit is the same as this unit, okay? After all of this calculation we have made, but we have to make it such that you're clear. It's not the same. We have divided by the density, and then we have put it in terms of million. It gives the same number, but you have to be careful where it came from. Okay, so we write that here, 3,500. Okay. That is read from the chart. Amount of water, that's, let's say, that's at standard conditions that I'm going to get. Here I have the rate of the field. Okay. So I multiply simply that by this ratio, right? That's what I'm measuring here. If here I have a volume, this volume is 20 million. That's how much the field is producing. I have the ratio between them, right? Simply I can calculate BWG. Okay, so simply Q of water at standard conditions will be Q of gas at standard conditions times this RSW. Okay, and that is how much for our case? That's 20 million. Okay, we can maybe use these units, 20 okay, times 3,500 standard cubic meter per million standard cubic meter, and we end up with 70,000, okay, per day. Is that a lot, or is that little, or how much is that of water that I have to process? A lot? How much liters of water is it? Times 1,000. So it's 70 million liters of water you have to process every day. I think we did, the calculation should be correct, okay? But it's a lot of water you have to dispose and treat every day. Okay, and this is just water condensing from the gas. Okay, so I think that we cut the class here. We have still to go through the other places. Okay, once you have, so that's key of water, we say that's this number times this number divided by 1 million. Okay, 70,000, which is a lot of water. And then we have to continue to the next one. Okay, why do we want to see what happens now? That's how much you have at reservoir, but then how much do you think you will have, how much that will change if you now make the analysis at the wellhead? Remember what I told you, what happens with pressure and temperature? The solubility goes down, right? The gas cannot carry so much water, okay? Therefore, it has to release it. It has to let it go. Here, it has a lot of water that it can contain and still be in gaseous phase, okay? When I come to 170 and 70, if you go very quickly, we look how much is it for 70 and 16,000. It's like 2,000, okay? So you're losing. Instead of carrying 3,500, you're carrying only 2,000. All the rest of the water has to drop out of the gas. It's not welcome anymore at the party. Okay, it has to drop, has to go out. It's not allowed anymore. And this water is the water that you have free in the system, that is causing corrosion, is causing hydrate, is causing slugging, all kind of things. Okay, so that's why it is important. So that's what we are going to do here. We are going to calculate how much water we have in every location, and then we calculate by the difference, we say that's the free water we have. Okay? But let's stop class here for today, and then we continue tomorrow. Any question before we close? Clear? Crystal clear? Okay. See you tomorrow.